impressive as that was, what does it have to do with math? Well, stay with me for a second and I'll show you. A 152mm M10T howitzer, which you just saw being used in an anti-vehicle role, fires a 40 kg shell with a muzzle velocity of 508 meters per second at a maximum elevation of 18 degrees. If the acceleration due to gravity is negative 9.8 meters per second squared, what is the maximum range? In order to solve this problem, we need two pieces of information. First, the velocity of the shell over the ground, which for simplicity's sake will not change. Second, the time that the shell is in the air. In order to find these, we turn to our old friend from last session, related rates. First, we need to find the horizontal and vertical components of the shell's velocity immediately after leaving the barrel. To do this, we consider the flight path as being the hypotenuse of a right triangle with one angle measuring 18 degrees. The speed of the shell can be represented as its change in position over time, or dv over dt, which we've already determined to be 508. The vertical component can be represented as the change in the height over time, in this case represented as dy by dt, and the horizontal component can be considered as the change in horizontal displacement over time, in this case written as dx by dt. Going back to the related rates concept that I mentioned in the previous project, we can relate dy by dt to dv by dt by using the sine function, and dx by dt to dv by dt using the cosine function as shown. Next, we need to figure out how long the shell was in the air. In order to do this, we start by determining an equation for the height of the shell with respect to time. And this next part is pretty complicated, so hopefully the errors I've added to the diagram will help you follow the process. We're going to start with what we were given. The acceleration due to gravity is negative 9.8 meters per second squared. This can actually be considered to be the second derivative of a position function for the height of the shell. Because the acceleration function can be considered the second derivative of the position function, integrating it twice should yield that position function. First, we take the integral of negative 9.8 dt, yielding negative 9.8t plus c. In order to determine what c is, we need to fall back on the information that we do know. First, we know that the function that we've just come up with is the velocity function for the shell. Second, we know what the initial velocity is. Because of this, we can take that function at 0 and know that that is equivalent to the initial velocity. Doing this will yield that c is equal to 157. We plug the c value back into the function we've created and integrate it again. Integral negative 9.8t plus 157 dt, yielding the position function negative 4.9t squared plus 157t plus c. By the same logic we used to find c last time, and the fact that the initial height is 0, we find that c is 0, yielding a position function of negative 4.9t squared plus 157t. Now we figure out the flight time of the shell by determining where it hits the ground, or mathematically speaking, where the position function is equal to 0 again. I used the quadratic formula to solve for the zeros of the equation and came up with negative 0.006, which would actually be 0, but because I rounded we lost some accuracy, and 32.047. From this we conclude that it took 32.047 seconds for the shell to reach the ground. We're almost done. Now we just need to figure out how far the shell travels over the ground. To do this, we use the formula distance equals rate times time, where rate is the 483 meters per second horizontal component of the shell's velocity that we determined earlier, and time the 32.04 seconds that we just came up with. Multiplying these two numbers together yields a result of 15,478.7 meters. What this means in terms of the question is that the gun is capable of hitting a target almost 15.5 kilometers away. However, due to the Soviet equipment having poor sighting systems, effective engagement ranges were actually closer to 3 kilometers. I leave you with an amusing historical fact. During World War II, Soviet troops used to play the song Katyusha over loudspeakers during artillery barrages to cover the sound of the fire, making it harder for the enemy to determine where the shells are coming from. I imagine that would sound something like this.